So we've defined row rank to be the dimension of the row space, and we've defined column rank to be the dimension of the column space. And it seems like those two should have nothing to do with each other. I mean, we've seen that if you have a matrix that's M by N, the row space of the matrix is a subspace in Rn, and the column space of the matrix is a subspace in Rm. So, I mean, these subspaces live in different Euclidean spaces, so it doesn't seem like there's any reason why they should have the same dimension, right? The row rank is the dimension of the row space, column rank is the column of the dimension of the column space. So why should the dimensions be equal if, like, they definitely aren't the same space, right? They live in different Euclidean spaces. Why should their dimension be equal? So it seems like there's no reason why those should be equal. But in fact, the row rank of a matrix and the column rank of a matrix are always the same. This is a big surprise. To see why this is true, we're going to have to think kind of carefully about what happens to the column rank of a matrix as you do row reduction, right? We know we can get at the row rank of a matrix just by doing row reduction, and this is nice because row operations do not change the row space. So, right, there's no worry about the row space because it never changes. But as we do row operations to row reduce a matrix, the column space will change. So we have to ask ourselves, if the column space is changing as we do row operations, what is happening to the dimension of the column space? So we're going to have to keep track of the dimension of the column space. So we're going to attack this problem in two steps. First step is to figure out what happens to the dimension of the column space as we do row operations. Okay, because right in the back of our mind we're going to do row operations until we get to reduced row echelon form. So as we do that, we'll keep track of the dimension of the column space, and then once we've gotten to reduced row echelon form, we will compare the row rank and column rank for the matrix in reduced row echelon form. Okay, so two-step process. So first let's do step one. What happens to the dimension of the column space as we do row operations? Well, remember that if we take a matrix A, let's call its columns A sub I. So these are the columns of A, not the rows of A, right? So A is A sub 1 as a column down to A sub n. Now, in general, these columns are going to be linearly dependent, right? They might not be in any example, but in general, these might be linearly dependent. But we know, when we learned about linear independence, we saw that if you have a linearly dependent set, so A1 through AN might be linearly dependent, but we know that if you have a linearly independent set, a finite linearly independent set, you can throw away linearly dependent vectors one by one until you have a linearly independent set. So, so let's take this collection of columns, throw away dependent vectors one by one to get a linearly independent set. And just for the sake of keeping my notation not crazy, I'm going to assume that all of the linearly dependent ones were at the end. If they weren't at the end, then renumber them. It's not going to change anything that follows if we renumber them so that all of the dependent ones were at the end. So when we do this, we get a collection of columns, possibly fewer than the collection we started with, right? We started with n of them, but we might have some fewer number left, so I'm calling that k. And this is linearly independent, and still spans the column space of A, right? We know as we can do this throwing away process, since we're throwing away just the linearly dependent vectors, that won't change the span. So all of the columns change the span. So all of the columns span the column space. So this resulting smaller collection also spans the column space. All right. Now, notice that we have actually come up with a basis for the column space. So, right, secretly, the column rank of A is k, is what we're saying here, right? Because we have a basis for the column space with k things in it. Okay. So now we have to imagine doing a row operation. So let's let R of AI be the result of a row operation. Okay. So let's imagine that. So suppose we have some linear combination of the AIs. A1, little a1 through times capital A1 through little a k through capital AK. And suppose that this linear combination gives us a vector. Okay. Well, if we do the row operation R, what we get is little a R of capital A, little a1 times R of capital A1 plus dot 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 plus little a k R of capital AK equals, so what shows up over here? Well, what shows up over here is the row operation applied to whatever vector was on the right-hand side. Remember, this is the case, so this linear combination is true if and only if this linear combination is true. And this is because much earlier we checked that row operations don't change solution sets to linear systems, right? So if the coefficient a's, the lowercase a's, are a solution to this equation, then they're also a solution to that equation, and vice versa. And it turns out this is the key we need to figure out what row operations do to the column space, or the dimension of the column space. All right, so you might wonder, well, look, right, we started that capital A1 through capital AK, those formed a basis for the column space of A. What about the row operation applied to the row operation applied to each of these columns? You might wonder, do these form a basis for the column space of the row operation applied to our matrix? Right? Remember, they definitely won't in general be a basis for the column space of A, because the row operation changes the column space usually. But they might form a basis for the column space of the A after we've done the row operation to A. Well, let's check. So to answer this question, we need to know, are these vectors the row operation applied to the first column, and so on, down to the row operation applied to the kth column, are these linearly independent? Okay, well, take a linear dependence relationship. right? So let's write a linear dependence relationship, maybe C1 RA1 plus dot 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 down to CK RAK equals 0. So here's a linear dependence relationship. Now, we know that if we do a row operation, this equation will still be true, right? That's what this up here says. If you have a relationship, if you have a linear relationship like this, if you do a row operation, that linear relationship either is still true or is not still true, right? These two are either true together or false together. All right, so what we can do is undo the row operation R, and that gives us C1A1 plus dot 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 plus CKAK. And what happens when we undo this row operation with the 0 vector? Well, if you do a row operation to the 0 vector, you get the 0 vector, right? But we know that the AI are linearly independent because we cooked them up that way, right? A1 through AK is linearly independent. That's how we came up with them. So we have a linear dependence relationship among linearly independent vectors. That means it has to be the trivial one. So that means C1 has to be 0, C2 has to be 0, all the way down to CK has to be 0. And that means that our initial linear dependence relationship up there is the trivial one. So we took a linear dependence relationship among these vectors, RA1 through RAK. We see it has to be the trivial dependence relationship. So that means these vectors, RA1 through RAK, are linearly independent. Okay. All right, well, I mean, so at this point, since we have a linearly independent collection, we know that the dimension of the column space of A after we do the row operation, right? We know it can't be any smaller than K because we have K linearly independent vectors. So this has to be greater than or equal to K, right? But suppose that it's bigger than K. So let's take but what if it's bigger than K? So let's take a vector V in the column space of the column space we get after doing the row operation. Okay, we know that we can undo. There's a row operation that undoes R, right? Which I guess I'll call R inverse. Okay, and the operation that undoes a row operation is itself a row operation. So R inverse is a row operation. Since V is in the column space of R of A, that means that we can write V is some linear combination of the columns of R of A. So V is C1 RA1 plus dot 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 plus C n RAN, right? We have to use all of these, not just up to K, but up to N, because, right, we don't know if the first k of these span the entire column space. That's what we're trying to show. So we know, so if v is in the column space, it's a linear combination of all of them. Well, if we do R inverse, right, again, we know that row operations don't change solution sets to equations like this. So if we do R inverse, we get the exact same equation, but right, the coefficients don't change, so still C1. Of course, when we do R inverse to this column, the row operation applied. Well, if we do the row operation and then undo the row operation, we just get A1 back, right? And so on, down to Cn R An, right, like this. Okay, but look, we know that the column space of the original matrix A is equal to the span of A1 through AK, right? Remember at the beginning we threw away the redundant or the dependent columns, so we don't need to write this vector, R inverse of V, as to write it as a linear combination of columns. We don't need all of these columns. We know that we can actually only use up to the kth column. Now, we might have to change the coefficients that we're using, so I'll switch to d's instead of c's, because the coefficients might change when we sort of get rid of the redundant vectors. But we know that it's possible to write this vector as a linear combination of just the first k columns, right? Because again, because we know that the column space is equal to this span. All right, so now we know that this vector R inverse of V is this. But now we can do R, we can hit this all with R again, and this gives us that V is equal to D1R of A1 plus dot 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 down to DKR of AK. That should be a K. All right, so this shows that V is in the span of the first column after the row operation down to the last column after the row operation. Okay, so what does this show us? Well, remember, V was anything in the column space of the column space after the row operation, and now we've shown that V is in the span of these vectors. Well, this span is clearly in the column space of the column space after the row operation, just because these are all columns after the row operation. So what we've just done is we've actually shown the inclusion the other way as well, right? So this means that the column space after the row operation is equal to, or it's spanned by, these first k columns after the row operation up to k. But we already know that these are linearly independent. So they're a spanning set, right? So we have a linearly independent spanning set for the column space. So these form a basis. So the dimension of the column space after the row operation is k. But look, way up here somewhere, right? We already knew that the dimension of the column space was greater than or equal to k. Well, now we know it's exactly k. Right? So the dimension of the column space after the row operation is k. But at the very beginning, we saw that the dimension of the column space before the row operation is also k, because we had this basis A1 through AK. So the upshot of all of this is that row operations don't change the dimension of the column space. Right? And the dimension of the column space, we call this the column rank. So row operations don't change the column rank. This is not obvious, because remember, row operations do change the column space. So they change the column, so the column space is changing the whole time, but the dimension of the column space is staying the same. All right, so this completes step 1. Remember, we had this 2-step process. Step 1, what happens to the dimension of the column space as we do row operations? It stays the same. Okay, so as we do row reduction to get to a reduced row echelon form, the dimension of the column space is staying the same, even though the column space itself is changing the whole time. All right, so now let's compare the row rank and the column rank for reduced row echelon form. Way down here. So compare row rank and column rank in reduced row echelon form. Remember, reduced row echelon form essentially consists of this stair-step pattern of 1s. Everything below and above the 1s in our pivot positions are 0s. Everything below the stair step is 0s. And we might have non-zero entries above the stair step that aren't above 1s. Okay, so what is the, let's call this matrix REEF for reduced row echelon form. What is the row rank of this reduced row echelon form? Well, we know that a basis for the row space of this is the non-zero rows. So here this is the number, the rank is the dimension of the row space, but the basis, how many non-zero vectors are there? Well, it's the number of non-zero vectors, number of non-zero rows. Okay. So the row rank is just the number of non-zero rows in the reduced row echelon form. So now let's think about the column rank for a reduced row echelon form. Oh, sorry, before we do that, notice that the number of non-zero rows, this is the same as the number of pivots. Right, because every non-zero row has a pivot in it. All right, so what's the column rank? Well, if you imagine the span, so what vectors can we get out of the span of these columns? Well, notice that every place where there's a pivot, these are actually standard basis elements, right? The first pivot, the first column with a pivot is actually E1. The second column with a pivot is actually E2, and so on down to some E. I'm going to call it EK. Notice also that the other columns, they can only have non-zero entries in entries where we had pivots, right? That's part of how reduced row echelon form works. And so to know the rank of the reduced row echelon form, right, this is the dimension. So dimension of the row space, dimension of the column space of the reduced row echelon form. Right, we need a basis for the reduced row echelon form. Well, these columns that aren't pivot columns, these don't add anything new to the span of the column space, right? Because this one is linearly dependent on that. This one is linearly dependent on those, right? This one is linearly dependent on those. So to get a basis for the column space, we only need these pivot columns. How many pivot columns are there? Well, it's the number of pivot columns. So for reduced row echelon form, the number of the column rank is equal to the row rank because both of them are the number of pivots, right? So now we're done, right? Big picture here is that the row rank, so row rank of a matrix A, I can't write row rank, there we go. The row rank of a matrix A is equal to the row rank of its reduced row echelon form, right? Because the row spaces are the same. But For reduced row echelon form, the row rank is equal to the column rank. That's what we just showed. And if we sort of unwind our row reduction to get back to the original matrix, the column rank of the original matrix is equal to the column rank of the reduced row echelon form, because row operations don't change the dimension of the column space. They change the column space, but not its dimension. So this we knew, this was step 1, and this equals, that was step 2. So this shows that the row rank of any matrix is equal to its column rank, which is a bit of a surprise. This gives us a really nice shortcut for computing row ranks and column ranks, right? So if we wanted to find a basis, also notice that as a result of our part of what happened in this whole argument is that, let's see, where can I point at to demonstrate this? These, I guess it was right here, right? When we're flipping back and forth between before a row operation and after a row operation, the columns that were linearly independent to begin with, those are still serving as a basis for the column space after the row operation. So we can ask, what columns, once we've gotten to reduced row echelon form, what columns do we need for a basis? Well, we need the pivot columns, right? So that the pivot columns form a basis for the column space of the reduced row echelon form. So going back to the original matrix, what columns would we need to get a basis for the column space? Well, it's the columns that end up having pivots in them. So all of this, not only does it tell us the surprising thing about column rank and row rank, it gives us a shortcut for finding a basis for the column space. We don't have to do a whole row reduction, right? That's a second row reduction to find a basis for the column space. So let me do an example and you'll see what I mean. So for a matrix A, let's find a basis for the row space and for the column space of this matrix. Now, before now, we would have had to do a row reduction to find a basis for the row space, and then we would have had to do a second row reduction. We would have had to reduce A transpose to find a basis for the column space. But we can do better than that now. Okay, so first let's do a row reduction. The result of row reducing this matrix is here. Okay, now we know that when we get to the reduced row echelon form, we know that the non-zero rows are a basis for the row space of the original matrix, right? The original matrix, because row operations don't change the row space. So the base for a basis for the row space of A, we can just take the non-zero rows. So that's 1, 0, 1 and 0, 1, 1. All right, notice that this tells us that the row rank of A is 2, because here's a basis with 2 elements in it. Okay, now let's find a basis for the column space of A. Now what we said before was that the pivot columns, any column that ended up with a pivot in it after the row reduction, we need those columns from the original to get a basis. So for our column space, right, since we have pivots in column 1 and 2, we take the original column 1 and 2. So 1, 1, minus 2, and minus 4, minus 3, 4. So here's a basis for the column space. And of course, this shows us that the column rank of the original is 2. And these are equal, as we knew was going to happen because we just proved it. Since the column rank and the row rank are always equal, we just call them the rank. So from now on, we'll just say rank, because we know it's this. That means both the row rank and the column rank, since they're always the same. Notice that to get a basis for our column space, we didn't actually take these pivot columns, right? So the column space here is not the span of the pivot columns themselves, right? Because these pivot columns arose after doing a bunch of row operations, and row operations change the column space. So these the columns after row reduction do not give us a basis for the original column space. We have to go back to the original matrix before we did row operations and pick off the columns that ended up having pivots, right? So in this, this shortcut for getting a basis for the column space, it's nice, but you have to be careful with it. After you do a row operation, you find a basis for the row space and the column space in different ways, right? For the row space, you just take these rows, but for the column space, you have to go back to the original. Matrix to get the appropriate columns. If you mix these two, it doesn't work, right? So if you think that as a shortcut you're going to take the columns from here, that won't work. Also, if you think as a shortcut you're going to go back to the original matrix and take the rows that have pivots in them, that also won't work in general. So you really have to take rows from here and columns from there when you're getting a basis for your row space and your column space. That's just a result of, since we did row reduction, how row operations affect the row space and how it affects the column space is very different. So you have to be careful to get them in the right order.